Alright then, so investigation of methods of heat transfer. There's 3, one for convection, one for radiation, and 2 for conduction. I'm going to use the conduction ring. So I got 3 different videos. Here's some diagrams. I'm not going to use the convection beaker, although I think I've actually got it in there. It's a while since I did the video, so I think it's in there, but we're going to use a ring because it shows convection better. We've got this setup for the radiation, and then we're going to use the conduction ring. So let's push on to the first video. The first video is for convection, and let's have a look. So I'm here with the heat transfer experiments. You can see there's one for convection, one for radiation, and then either one or the other for conduction. So this is the apparatus for convection, which we're going to concentrate on first. So they want us to use potassium permanganate and then drop it into a beaker just like this. So here's our method. You can see that we've got to record our observations to see what's happening. But we've got this thing called a convection ring. If you just move out the way, sir.
Sorry, sir.
It's all right. This should show the movement of potassium permanganate around this tube. So here's the chemical. It's like a deep purple chemical. We haven't got forceps, but we'll use a bit of a spatula, but we don't want too much, because if we put too much in, it's got more chance of diffusing then, and we want to see as little as possible so we can watch it going around. Could do with a nice dark background, but okay, are you ready?
About that much, yeah?
Go for it. Well, I would say even less than that.
Even less, yeah?
Yeah, you just want a real, that's it.
About that much?
Yeah, go for it.
Always have more, can we?
So we've got this warmed up. Hopefully you'll see it straight away. And
here we are.
There it goes. So you've got the heat source there. It's moving around. So it's sinking at the moment, which means the water here at this point, if I get my finger, don't want to burn it.
Do you want me to up front?
Yeah, so the water there at the moment is less dense. That means the particles got mega energy, so they're moving apart, and that heat will rise. So the less dense particles will rise and start moving, displacing the more dense particles at the top. You can see that purple sort of coming around. It's almost like a bus journey. Maybe put a bit more in, sir. Maybe I was a little bit careful.
Yeah?
I was a little bit careful there. Go for it. Go on, treat yourself. There we are. Oh, you're going for it, man, didn't you? See, you've done this before, haven't you?
Here we are. It's not my first rodeo.
No, it was my first rodeo. That's what you want. Mr. Timothy was being a bit careful there. So yeah, it's sinking now. So it's cooling. So one of 2 things happening now. The particles are either cooling, so less energy, and they're sinking, so they're becoming more dense, or this part here, point for me, sir, because I can't see, because I'll burn my finger. They are displacing the denser particles, so they're moving them down. So our main thing here is to know that less dense particles with more energy at the heat source is going to rise and displace the more dense particles.
And just to remember then that this is just in liquids and gases, yes sir, not solids?
Fluids, yeah. Just put a little bit in, sir, so we can see the one that the...
Let's just get a convection curve and put it right on the corner.
Right on the corner, I would.
Heat him up then. Heat him up.
And then we can see that convection current then. Just out of interest, while sir prepares that, you can see that this is slowed right down now because we've removed the heat source.
So we go, we're ready, sir. We're ready.
You ready? Go for it then. Let's have a look what's happening here. Here it goes. Boom. And away, straight away from the heat source. You can see you don't really get so much of a current going there.
We are seeing though it is twisting round. It is rising and falling and twisting round a little bit. It's not as good in the beaker though, is it?
Oh, I don't think it is.
I prefer the convection ring one.
Yeah.
If I was going to pick, I would do the convection ring.
Lovely. I got a nice close up of the window there.
Just that nice clean window.
Yeah.
Brilliant, man.
We can get Malcolm to sort that out, can't we?
Our Malk is watching things for safety, so yep, that's convection.
And then I've got the video for the radiation one now, so that's next.
No,
Yeah, that's fine. Go live. So this time we're going to do this radiation experiment. There's only one that you need to know, but I'm going to show you two anyway. The method is fairly easy. Okay, so we sellotape some black tape. So if you look at the thermometers there, some black tape and some tin foil to thermometers. Let me just jump in front of you there. I've used a ruler to measure out distances, because obviously that's going to be a control factor now. These thermometers need to be exactly the same distance from this filament lamp, this heat source of radiation. So this is radiating heat. And you will see that black is a good absorber of heat. If it's a good absorber of heat, what's going to happen that the tip of the thermometer, which is mercury, is going to get warmer than the one with foil, because the one with foil should be reflecting that heat back out. So it's a good reflector. So it's a poor absorber.
Quick question, sir, just what I thought of. How could we make this more precise? Just a little link to our practical stuff. How could we make this more precise, maybe?
I would say the resolution on the thermometers could be higher. So you could, instead of going up in ones, it could go 0.1s. Obviously, the distances, the controls. That's pretty much. Can you think of anything, sir? You kind of put me on the spot there.
No, so it was just a suggestion, sir, because they may throw that in an exam. Or
Yeah, I think the biggest thing here is going to be inaccuracy, because obviously if this heat source changes, and you need time to warm these up essentially. So this has been going a while now, so I can turn this off. But
so if I just show you, so we can see with the black tape, the good absorber, we've got around 40. And then with our silver, the reflector is 30, so a huge difference there.
And the other one that we usually do inside, but it's not in your prac. I mean, we would usually fill these with the same temperature water, and we could see then how much they actually emit heat. So the silver one is likely to reflect the heat back in from the boiling water and would retain its heat. And the black one, which is a good emitter, would lose more heat. And these can be used both ways actually. You could also use these, if you had enough time, with a heat source. So let's pretend we had this filament lamp back on and we had these two clamped with same temperature water. How much would they warm up? So we can take the temperature difference there. And I'm guessing this one wouldn't warm up as much as this one, because this is a good absorber of heat and this is a good reflector of heat. But by the same principle, we could put same temperature water inside. This one would lose more heat because it's a good emitter of heat, and this one would trap more heat, so it would be warmer because it's not a good emitter of heat. And that's why when you've got a flask of coffee or a flask of tea, they're not going to use black materials, they're going to use shiny, bright materials. And that's pretty much it for radiation.
And then if we just do the last video then, which is the conduction ring.
Are we live?
Yes, we are live. So the next one I'm going to do is this one. We can see what we've got, the conduction ring here. This one is slightly harder to do because, well, we've got the materials, but they haven't, you can see they're very old and they're not labelled and we're not sure which metal's which. But the same principle applies. You get some petroleum jelly, some Vaso, you put them on the ends, you put paper clips. Important here that all the paper clips are the same size, because if I had smaller paper clips, different mass, they tend to fall at different times.
So just to check then, so we've got different metals on here. We say we've got copper, iron,
yes,
brass and aluminium.
And I've done a small table of results here. A very small one, a very simple one, that we can hopefully take some results from this. It shouldn't take long. My stop clock, unfortunately, Again, to improve it, you can see that it only goes 1, 2, 3. We can improve the resolution of that. We could make it more accurate if we went to decimal places, but it's all I've got at the moment. And I'm going to place this heat source now. In fact, I need to bring this closer, don't I? Now, it's important that I put it directly below, so every metal has got the same amount of heat being applied. So I'm going to try and press start as soon as I put it under, and I'm going to hit the blue flame, and let's watch what happens. So there's my stop clock. I'm going to predict that copper is going to go first, because copper is a brilliant conductor of heat, and then it's anyone's game after that. Probably there. So there's copper at 21 seconds.
Ah, so it melts the jelly, does it say?
It does, yes.
So the better the conductor, the quicker the paper clip will fall.
So the heat's transferring from the cold end to the warm end.
Oh,
My marker's still
brass
on fire.
is gone. He's gone.
Brass is gone.
Oh, aluminium's gone.
Brass was gone at 43 seconds. My marker is still on fire.
Iron's going.
I need to extinguish my marker. It was on fire.
Iron's gone.
Okay.
And
we didn't have any time for
brass
that
is gone.
because the marker was on fire. But don't tell anyone.
Aluminium went straight after brass, sir.
Did it?
Yeah, aluminium was about 45.
So that's in the correct order there.
Yeah.
And what's well, we can compare it now. Let's have a look what they'd expect. They've got the expected results here: copper, aluminium, brass, and then iron. So
we're a little bit of a switch in the middle, but just about.
There, yeah. I'm not going to touch that now because obviously it's hot. That's going to retain its heat. Ways to make this more accurate, I suppose. The positioning of this heat source, just to make sure each one has an equal amount of heat, because this might have been a little bit edging towards iron. I couldn't really get under there because of the stretch.
Can we just talk through what happens in the metal again, sir? Why the end gets hot?
The end gets hot, so you're applying. So conduction happens in solids. So you can imagine two particles touching. I've tried to set this up to see if we can represent it with this, but basically you're going to be passing energy from one end, from the hot end to the cold end. All these particles are going to excite one another of their neighbouring particles. So the energy that you put into one particle is going to start exciting the neighbouring particle, and it's going to transfer that heat from hot to cold. And that's conduction. It happens in solids. Metals are good conductors. Plastics are good insulators, so they're not good conductors. And there's my phone.
Here you go.
So the one thing I forgot to say there was that metals have these free electrons as well, which help it transfer the energy. I did at one point in the video say that heat was passed from cold to hot, but I think I was more concerned with the marker being on fire. There is some safety hazards and risks with this experiment, so if you just you can always quickly read that. That's unlikely to come up in an exam though. It would just be mainly how you can improve that experiment, or what things need to be controlled. The other thing was the distance or the length of the metals need to be the same really. It's no good having copper 26 centimeters and then aluminium 40 centimeters, because it's just not a fair test then. So metals need to be the same length, and I would also say the same amount of petroleum jelly on each paper clip. So just to make things really fair in that test. And you could repeat that a number of times then to validate and get rid of those anomalous results, to improve your accuracy and to check repeatability.